And now we're up to our third and final presenter, Zhao. Am I close to pronouncing that? He's presenting us a product called TrajAnalytics. I'm also going to have to double check the pronunciation of that, TrajAnalytics. It's written as one word. It's a web-based visual analytics software of urban trajectory data. So Zhao is a professor in the Department of Computer Science at Kent State University in Ohio. His current research interests include visual analytics of urban data, information visualization, and deep learning visualization. He has been supported by NSF to develop several open source software of urban data visualization. There's a theme there, right? So thank you so much for joining us. Come on up.
Thank you for the introduction, everyone. Welcome to this, I think it's the last talk in this symposium. Okay, let me see how to forward this. Oh, thanks. Okay, I will talk our work. TrajAnalytics is a software supported by NSF. So right now it's open source. In general, we are trying to, let me see. Okay, to handle this urban trajectory dataset. Usually, I think all of us know that it is a sequence of sampling points based on GPS or maybe other types of sensors that usually including the locations as the longitude and latitude and the speed, date and time, or maybe sometimes it also involves some other associated information. So we try to provide a tool to help people process and visualize such data set. So we can collect such data sets from different types of resources. Mostly we have is from the vehicles like the taxi data sets, but also we have some data set as a personal trajectories, as well as some mobile phone-based that is collected by the cellular stations, as well as right now if you enter a building, you connect with the access points of the Wi-Fi system, you also possibly be tracked of your location inside this building. And all these kinds of, or even the social media right now, sometimes they also have the geotagged information. If you connect this geotagged information of these messages, you can also get the trajectory information. Okay, so it has been a lot of work on how to utilize such trajectory data set in urban study to try to find the information hidden in the massive population mobility data so that we hopefully can find the patterns and to optimize the assessment and planning of the transportation systems as well as other urban infrastructures. And so finally we can improve the quality of life and the environment of the citizens. So it has been used in, of course, transportation, but also other fields like the urban planning, even energy, environment, or even crime, and other business applications. So in particular, from data point of view, such data usually have spatial properties, and we have the moving object in these geographical spaces. And also, we know we have to, most cases, to link this raw data to the road networks, to the interested regions or the points of interest, like the buildings and the shops, all these kinds of information. Meanwhile, it's a dynamic data set. It also includes these temporal attributes, especially the human population movement. We have the periodic patterns for every day or for every week, and also these different trends in different time periods. Those kinds of properties all have to be visualized in some way. Okay, a little bit on the availability, and we are in the university, and it's a little bit tricky to get this kind of data set. We collect many public available data sets. Mostly it is from the taxi and public transit data sets. We know that somebody or some companies or some other administrations, they have these different types of these kinds of trajectory data, but because of the sensitivity or the other issues, it may not be easy to get that. So that's some experience from us. In general, for visualization, our major purpose is try to support the interactive data exploration so that people can look at this data set and hopefully can also perform analysis over this interactive interface. So mostly we have two parts. One is we need to design different visual representations. The second is to provide its interaction technologies. It has been a lot of work in the field of visualization. People try to visualize the trajectory data sets. Usually, I didn't list here, mostly it can be considered as three different categories. One is to directly visualize the trajectory itself as starting points and end points, or even the polylines connecting these traces. The second is to project this data over the spatial units, such as streets, regions, or countries. The third one is the flows among different units between different regions or from this street to that street. So this is two different types of visualization tasks for these trajectories. So here I will present our goal for this software. In particular, we got support from NSF to support the researchers or the analysts in different sectors to perform this data-driven analysis and try to provide open source software for visualization. So in particular, we will provide these iterative data exploration functions through these interactions together with the visual interface. Okay, so from the computer science point of view, this software needs to integrate several things. First is we need a relatively powerful computing platform because we want to make this as a web-based. So we need a server which can handle relatively, because this data can be very huge, relatively massive data set, and also provide an easy access gateway so everyone can access this data set if you install it on the server, on the cloud, so you can access it through any internet browser. And also we need to provide a good data storage and management function so that we can, because most of the visualization is based on the data queries, so we want to handle this multiple and the different types of these queries to return these queried results as soon as possible. And finally is to provide this exploratory visualizations. Okay, so these are the summary of what we are doing now. That is, mostly we can separate this software into three parts. One is to data preparation, pre-processing, because we try to be able to allow people to upload their own data set. You know, that could be any format or whatever. They have a lot of, this kind of data has a lot of noises or errors, so there's always a headache. You have to clean the data and to perform this matching from your raw GPS data to the different urban structure data sets. That's one thing. Another thing is we need to do data aggregation, like we want to project this raw massive trajectory data over the street segments and over these regions. And also need to transform this kind of data to a particular format we need to process inside our database. The second module is data management. We develop a special database, build a special database. It will need to handle this heterogeneous data set, and we need to define some spatial indexing and temporal indexing structures inside this database to support this fast query. And then based on that, we consider what kinds of queries we need to support and to combine this, mostly these different types of spatial queries together with the temporal constraints. Then finally, on the website, we provide a visual interface that we need to integrate this map visualizations, different types of maps, and together with its different types of charts, diagrams, its information visualization graphs. And finally, to combine some, there are some issues on how to provide good interactions to the users. Okay, so this is a framework. So we build a database, and people can upload their trajectory data set through our web-based interface to the database, and then can access this database through these different types of queries. And finally, this query will return the results to the website so that people can observe and interactively conduct this visualization over this data set. Okay, so first we need to process raw data. The users can upload the raw trajectory data. Of course, we cannot handle all kinds of formats. So right now we require users to convert this data to the, most of the data is in the raw data is in CSV format, or sometimes in JSON. So you can support these different types. And then it's a little bit tricky in practical use because, for example, the longitude and latitude that representing locations may have a different name in your database, in your data file. So we have to ask people to tell me what is a real name in your data set. Then we need to do a match and do a little bit cleaning to remove maybe some incomplete data set over that. Another thing is we try to support this map matching, that is project this raw data set, raw points to the geographical units, such as streets, such as regions. So right now we allow people to, we can help people to automatically download street networks based on the data set you upload, then perform this GPS map matching. Meanwhile, for the regions, we provide two types of region matching. One is the zip code regions. In the United States, it's available, it's public, but in other countries, maybe not. Even in Europe, only some countries have this public available zip code region geometry available. So we also provide a way that you can set up the grid cells so that you can define the different resolution of grids, so you can perform this aggregation of the raw data also over this grid cells. So after that, we process the data and store it to the database on the server side, then provide these trajectory queries. So at this moment, we support different queries. That means you can draw any arbitrary region as a polygon or as a circle or whatever on the map interactively. Then this spatial constraint will be transferred to the database through these four different types of queries. One is start, one is end, one is path, another one is content. That is to consider that, for example, all the taxi trajectories starting from around this building, or all the trajectories ending at this building, or maybe a special region that this trajectory is passing this region, or maybe this trajectory is totally contained inside this particular region you specified. So after that, this is the four different types of queries. And meanwhile, of course, we support these joint queries because most cases I want to find the trajectory starting from region 1 and at region 2, or maybe even parsing another region in the middle, so people can combine these different queries together through these typical Boolean operations like the union, difference, and intersection. Sorry, it should be intersection, not interaction here. Okay. So after that, inside this database, we implement some data indexing structure. It's mostly like when you read a book, you can go to the index to find the words, so you can immediately find which page it is on. So in the database, we still need these kinds of things because otherwise, if you query a region, I need to go through all this data to find which one is inside. It's so slow. So we need to provide some spatial indexing structure there. And after that, we perform the data aggregation. That is to map, for example, I want to know at a particular day or hour how many trajectories passing this particular street segment. I need to perform some pre-computation over that. Okay. Now this needs to handle some challenge, that is interactive performance. And also we need to perform this web and cloud interactions through this internet. There are some issues for communications. So for database, we use this open source PostgreSQL database. They have a good extension to support this GIS spatial query and indexing. It's called PostGA Extension. Okay, so after query, we do this spatial aggregation over the rows, POIs, regions, and also meanwhile, you can also do this over the weekdays or days and hours. So this is the interface to show in the left, it's it's a map view, and also there is a manager because people can query multiple times, right? I can combine them, or I can delete them, or it's also very important, I can save them because I might share with my colleagues, or I want to come back tomorrow to load it. On the right is the visualization. We show the list, and you can rank the query results based on speed or length of this trajectory, as well as provide this tool. Right now, this shows two charts about this distribution of your query results over different hours or over different days. Okay, these are another view that shows we can map. This is aggregation results. We show the heat map that is to, in particular, is the start points and the end points of this taxi trajectory in the city of Porto in Portugal. Okay, this is another example to show that on the top is we aggregate this trajectory results over this street segment to compute the traffic speed. On the right, we visualize the traffic flow over your query. And on the bottom line is to, instead of mapping to the street segments, we can also map to a particular grid cell, grid structures. Okay, this is to show on the right is the different charts. We already showed for the temporal distributions. Okay, in system implementation, we use some existing. This mostly is about the interface. We use some available. The leaflet is the best map support JavaScript library. And this three is widely used interactive visualization tools based on JavaScript. Okay. Finally, we show this example. This is to show that you can load your data set. Meanwhile, this is a web-based system. Right now, we have this server on our own department. But meanwhile, we have a lot of feedback that people may not want to share or upload the data. So we also provide a local version that you can download and install on your machine. But you need to do some configuration to open your web server on your local machine, but it's totally on your machine. So it's very good. So you no longer need to upload your data to our server, and you can process in your local machine. So anyway, this is the process that you upload your data, do some pre-processing, and then we show the example of map matching. So this one is to, okay, so anyway, because it's a cloud-based system, so you also have a lot of issues about the user account management, all these kinds of things. Because different users may upload different data files to the database, so we also need to make sure it's correct. So this one shows that after you upload your data, we automatically compute a bounding box to cover all your data set, data points. So you can adjust it, because sometimes you have an error. Maybe there is a point far away, you don't really care, so you can shrink or adjust this region, and then our software will automatically extract the road network geometry from the OpenStreetMap in API, then to download and create another data table to attach to your file inside the database. So this one shows that it's the street network we already downloaded here. It also have different levels of the street networks. So we have so this part is sometimes it's slow because you need to do the processing. Okay, anyway, I don't have time, but while it's still playing, I can answer questions now. Yes. Okay.
Well, first of all, thank you very much for your presentation.
Yeah, thanks.
And if anyone wants to ask a question while we watch the rest of the demo, please step up to the mic.
Thanks for the presentation. I'm curious about the map matching tool. Could you talk about what algorithms you're using? And I'm also curious if you could support map matching that is mode dependent. You know, like if it's a bicycle GPS, it would need a specific type of street network versus a car.
So actually, this road net map matching is a research topic, right, in GIS field. So we just implement one of the algorithm. It's not the newest one, because the newest one, they even use some artificial intelligence to predict this one. So we just use a little bit, it's like project the point to the roads. Because the road network we download is actually the geometry, like the line here. So we just project the points, a sequence of points to this line segments. That's the method we use, but actually there are some algorithm inside, not very complex.
You're not taking into account direction or speed, it's just...
Yeah, we consider that a little bit. Not, the newest one, they use historical trajectory information to predict this person. 90% they will go this road, 10% will go this road, then they do something. But we didn't use that, just some geometry-based method. Yeah, but we consider the speed a little bit. Yeah, yeah.
Which algorithm are you using?
I don't know the name. It's my student implemented by themselves based on some paper. So I can check details for you. Okay, so this one shows that you can query any arbitrary regions to visualize the results.
Any other questions? I was curious if this would work with pedestrian data, car data, bicycle data.
Yeah, we tried different types of data. Right now, this demo we show here and also online is we can mostly handle the city level. We are trying to extend it to a larger level, for example, for the airplane trajectories. So that we are working on something like that.
Last call for questions? All right, well, thank you very much.
Okay, thank you.
And a special thank you to Will for actually asking questions for all three presenters. I think one of the great reasons of coming here in person, right, is so we can convene and have a dialogue. So that's very welcome. And for those of you who missed it this morning, Will presented his project, very interesting. And I think you can get more information about that by following him on Twitter at wgeary, G-E-A-R-Y. Oh, and don't forget, by the way, we have like a secret Twitter account for the Data Visualization Committee. That's TRBVIS. It's not too late to tweet the event. And with that, I adjourn us. Thank you so much for coming and participating, and we'll see you in 2 years.